Good morning, lads and ladies. Fabrice, looks like you're the only one here so far. I'll give a
Yeah,
few more minutes for other folks to show up so we can get rolling. I know I was a few minutes late posting that link. Oop, cannot minimize. Okay.
right.
I do need to update this. And then we'll get started. I do hope more people show up. I know it's the day before Thanksgiving, but good, okay. All right, well, we're getting there. Folks are trickling in, so while you guys trickle in, I'll go ahead and switch over to the dot cam, get us started. Watch out, Cammy. I need you to move, Bubba. I gotta scoot in. Yeah, I know. I know. You're very cute. Okay. So today we're going to talk a little bit more about matrices. Last time I showed you guys how to rewrite a system of equations as a matrix, and we talked about row reducing those matrices to solve the corresponding system of equations. Today I want to talk a little bit more about matrices in general and just look at what matrices are kind of as their own thing. We're also going to talk a little bit more about the relationship between the system and its matrix, but I just want to focus on kind of vocabulary, terminology, things like that. So this is MAC1140, section 4. It's a lecture, and today is the 25th. So I want to tell you guys that I appreciate you coming, even though it is the day before Thanksgiving. Clearly, not all of your classmates have the same dedication, but I'm really, really grateful for that. It's a nice, simple sign of respect to show up on days when we have class. So thank you for doing that. Today, we're going to discuss matrices and their properties. So I'll say recall that an M by N matrix is a rectangular array of numbers. We usually denote them by capital letters like A equals 1, 0, 3, 2, 0, 1, 1, 7, 1, 0, 2, 3. This is a 1, 2, 3 by 1, 2, 3, 4 matrix. So the first number is the number of rows. The second number here is the number of columns. And we saw last time how to take a system of equations and write it in a matrix. Yeah, so Lily, we did mention this. Our last exam is going to be on the last day of class. You're in this section here. You guys' last day of class is next Wednesday, which is December 2nd. So your very last midterm exam, last regular exam, is going to be Wednesday, December 2nd. I am still working on getting the exam 3 stuff sorted out, so I apologize. I know you guys have been a little bit more patient than you normally have to be, but it's a busy time for me like it is for y'all. So our last exam, which is going to be just on the stuff we've covered since exam 3, will be next Wednesday. I may end up doing a take-home test for your last test. I haven't really decided yet. It depends on how badly I want that day as a lecture day. While we're here, let's go ahead and get that out of the way. While we're here talking about exam dates. So exam 4 for you guys, your last exam, would normally be this week. But we've lost a little bit of time due to holidays and stuff like that. So I'm going to push it back as far back as we can, which is next Wednesday, because that's your last day of class, and it may end up being a take-home. So exam 4, expect to get that next Wednesday, either as an in-class exam or as a take-home. And then your final exam, go ahead and put this in your phones, calendars, whatever's right now, with a few warnings, notifications, alarms. Your final exam is December 7th, which I believe is the following Monday. Yep. At 3:30, which is a weird time for us. Okay, matrices. The first number in the dimension tells you how many rows. The second number tells you how many columns. So this matrix with 1, 2, 3 rows and 1, 2, 3, 4 columns is a 3x4 matrix. You've seen how to take a system and put it in matrix form. What I want to start introducing to you today is just kind of the land of matrices. It turns out one of the things mathematicians love to study are spaces. And speaking very abstractly, a space is just a collection of mathematical objects that all kind of have the same properties. And one of the important spaces that mathematicians study is the space of all matrices. Another one is the space of all real numbers. That's a set you guys are familiar with, right? An algebraic set together with some properties. The real numbers form, well, it's called an algebra. There is also an algebra of matrices, and it is a beautiful thing. But in order to talk about it, we need a little more vocabulary. And the first thing we need is this concept of dimension. If a system of equations has infinitely many solutions, then we call it a dependent system. This is because the rows of the corresponding matrix will be, the word here is linearly dependent. What linearly dependent means is that you can multiply, you can add up combinations of the rows to get one of the other rows. For example, the system x minus y plus 2z equals 1, and let's say 2x plus y plus 0z equals -2, and 3x plus 0y plus 2z equals -1. This is a dependent system. Meaning it'll have infinitely many solutions. And one way to see that is by considering the matrix 1, -1, 2, 1, 2, 1, 0, -2, 3, 0, 2, -1. I always like to put in this line here to remind me which piece is coming from the coefficients and which piece is coming from the right-hand side, but you've probably noticed that your homework doesn't do that, right? They omit this vertical line. But what I mean by dependent is that the rows of the matrix are linearly dependent, meaning here, if I can use some combination of the first 2 rows to get the third row. Here, row 3 is equal to row 1 plus row 2. So it's possible to get row 3 as a combination of the other rows. Any such matrix corresponds to a system with infinitely many solutions. So we call the system dependent because the rows of the matrix are linearly dependent. You can build one as combinations of the others. So this means the matrix rows are linearly dependent, and that means that the system is dependent and that means that the system has infinitely many solutions. So just a little bit of vocabulary. A system which has infinitely many solutions is called dependent. One way to check for dependence of a system is to see if the rows are linearly dependent. Can you get row 3 as a combination of rows 1 and 2? And here it's obvious. If you just add row 1 to row 2, that's exactly row 3. So the third row is linearly dependent on rows 1 and 2, which means this system has infinitely many solutions. So one of the questions in your homework just asks you to classify systems as dependent or independent. Independent systems so a system with a unique solution is called independent, meaning no row in the matrix, in the corresponding matrix, is a combination of other rows. And finally, there's a special name. I want to make sure I use the same vocabulary that your textbook uses for systems with no solutions. A system with no solutions is called inconsistent. And while there is a relationship between this statement and the matrix statements here, it's a little bit complicated. It means that the rows to the left of the vertical bar are dependent, but to the right of the vertical bar are not dependent. So it's a little bit complicated. Rather than saying that, I just want to make sure you have this vocabulary. Independent is a system with a unique solution, and it corresponds to a matrix where all the rows are linearly independent. A dependent system is one that has infinitely many solutions, and it corresponds to a matrix whose rows can be used to build up the other rows. And an inconsistent system is one where you can row reduce the matrix to something like 0 equals 5. These have matrices which can be row reduced to something like 1, 2, 0, 5, 0, 1, 1, 7, 0, 0, 0, 2. So if you've got a row of all zeros here, but then a non-zero thing here, when you go to put into that upper triangular form, then this is inconsistent. Because the last equation, the last row, tells us that 0x plus 0y plus 0z should be equal to 2, which is impossible. Okay. Row reduced. Yeah, after the words can be there, this is the word row, R-O-W, and then the word reduced, R-E-D-U-C-E-D. So row reduction is the thing we were practicing last time on Monday, where you do row operations to get a matrix into a form like this. There are some special forms for a matrix. We've already talked about upper triangular. This is where your matrix has something like, numbers up here like 2, 1, 0, 3, 0, 2, 7, 5, 0, 0, negative 2, 4, something like this. Where if you kind of look along the diagonal, everything beneath it is 0. So an upper triangular matrix is one where everything beneath the main diagonal is 0. The main diagonal are these pivots, right? So once you get a matrix into upper triangular form, then you can start reading off the solutions, right? Here, from this bottom row, I would get negative 2z equals 4. So divide by negative 2, z is negative 2. And then you'd back substitute into the equation from this to get y, and then you'd back substitute both of those into this to get x. So if you're trying to solve a system, once you get the corresponding matrix into upper triangular form using row operations, we're pretty happy. There's two other special forms. One is called echelon form. And this is the same thing, just where the main diagonal is all ones. So like 1, 2, 3, 7, 0, 1, negative 1, 2, 0, 0, 1, 3. This is called echelon form because everything beneath the main diagonal is 0, and the main diagonals are all themselves 1. And we've talked about this also. There is one more form that we haven't talked about called reduced row echelon form. And that's where these are all ones, everything beneath is 0, and everything above is 0. Reduced row echelon form is the easiest way to read off the solution, but it's the hardest to get. Where the main diagonal is all ones and everything else is zeros. Everything else to the left of this bar. So for example, like 1, 0, 0, 2, 0, 1, 0, negative 5, 0, 0, 0, 3. So this is in what's called reduced row echelon form. Oh, sorry, this should be a 1. Reduced. R-E-D-U-C-E. Oh, I said reduces. Reduced. The reduced row echelon form, this form, has some importance because there's the name of this matrix is called the identity matrix. So before I move on, I just want to make clear that if you're trying to read off the solutions to a system, the reduced echelon form is the easiest one to work with, because this bottom equation just tells you 0x plus 0y plus 1z equals 3. So z is 3. This tells you 0x plus 1y plus 0z equals negative 5. So y is negative 5. And this guy tells you that 1x plus 0y plus 0z is equal to 2. So x is 2. In other words, if you get the matrix into this form, then the solution to the system is just these numbers. Real convenient. But of course, getting it into this form is more work than getting it into this form, which is more work than getting it into this form. And we can also read the solution off from this form. It just takes a little bit more work. So it kind of depends on how badly you want to stay in matrix land to do your work versus staying in matrix land for as little as possible and then going back to the equations to do your work. Upper triangular gets the job done. Reduced echelon form gets the job done a little bit faster, a little bit more efficiently, because you can just straight up read off your solution as x equals 2, y equals negative 5, and z equals 3 without ever writing a system of equations back down. But the row operations you need to do to get to this is more than the row operations you need to do to get to that. So you won't see me going all the way to reduced echelon form on examples in class. It just takes longer. Computers, however, are pretty good at doing this. And if you have a TI-83 or whatever, TI-84, 89, they all have matrix modes. You can feed it a matrix and tell it to put the thing into reduced echelon form. Calls it RRED, reduced row echelon form. They're great at it. And there's lots of matrix calculators online. I don't want to say any more than that. Computers are better at this stuff than humans because it's lots of little calculations. The matrix, the square matrix, (1, 0, 0, 1), or I should say matrices, because I'm going to talk about a bunch of them. 1, 0, 0, 0, 1, 0, 0, 0, 1, and like 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. These matrices, where they're not augmented, they're square, and you've got ones on the main diagonal and zeros everywhere else, these are special. This one is called I2. This one is called I3. This one is called I4. These are called identity matrices. Not having anything to do with trig identities, these are called identity matrices because if you multiply a 2x2 matrix by I2, you'll get the 2x2 matrix you started with back. If you multiply any matrix by the same size identity matrix, you will get the original matrix back. To make sense of that, I need to tell you how to multiply matrices. So that's the next thing we're going to talk about. I just want to take a look and make sure I'm not skipping over anything that you need for your homework. So give me just 1 second. Take a look at that, because I don't want to leave you stranded. Yeah, when I'm solving these by hand, I always go for the upper triangular matrix. I never waste time going all the way to reduced row echelon form. It's just more opportunity to make mistakes. Yeah, okay, that's all we're doing this week. So identity matrices. So what I'm about to show you, you don't need it for this week's homework, right? What we did last time, those examples, that's everything you need for this week's homework. Today, this is just terminology. The first few things we did here where I told you what a dependent system, independent system, and an inconsistent system are, there are some homework problems about that. But starting now, I'm showing you things that you'll need for next week. In the sense that if A is a 3 by 3 matrix, then I3 times A is A, and A times I3 is A. In other words, if you multiply a square matrix by the same sized identity matrix, so if A is any 3 by 3 matrix, then when you multiply by the size 3 identity, you get A back. In other words, these matrices correspond with the number 1, right? These are like the matrix versions of the number 1. So if you multiply any number by 1, you get that number back. If you multiply a matrix by an identity matrix, you get that matrix back. But how do you multiply matrices? Matrix multiplication is complicated. First, you can't just multiply any two matrices. You can only multiply matrices together if a certain size criterion is met. You can multiply an M by N matrix with a P by Q matrix only if N is equal to P. And the result is an M by Q matrix. And I really wish I had more time to talk with you guys about matrix algebra, but we are limited here. I'm going to show you how it's done, though. We're going to start by showing you how to multiply some small matrices. So the trick here, it's done by looking at rows of the first matrix and columns of the second. So here's how you multiply two 2 by 2 matrices. Here, this is a 2 by 2. This is a 2 by 2. So M, N, P, and Q are all 2. So it is true that N is equal to P. And it is true that the output will be another 2 by 2 matrix. I look at rows of the first and columns of the second. So here, I take this first row and this first column. That will tell me what goes in the 1, 1 position of the resulting matrix. It will be A times E plus B times G. If I want to know what goes in the first row, second column of the resulting matrix, I take the first row here and the second column here. A times F plus B times H. If I want to know what goes in the 2, 1 position of the resulting matrix, I take the second row of the first matrix and the first column of the second matrix. C times E plus D times G. And then over here, I'll take the second row and the second column. So that's CF plus DH. This horribly complicated operation is how you multiply 2 matrices, specifically two 2x2 matrices. But matrices don't need to be the exact same size in order for you to multiply them. This is a 2x2, and this is a 2x2. What I need is that the inner numbers match. So here, the number of columns of the first, n, is the same as the number of rows of the second, p. And then I form the product according to this rule, where you take rows of the one with columns of the other, and you multiply down. So let me do another example. Let me do one with an identity matrix. Oh no, I'll do something with a non-identity matrix first. I'll let you write this while I pull up an example here. State the dimension. Boring shit. Come on. Yeah. Just gonna multiply 2 matrices. It's a 2x2. It's a 2x3. All right. Which one have you? So I'm going to show you how to multiply a 2x2 and a 2x3. I'm going to do it through an example. If A is the matrix 1, 3, -1, 0, and B is the matrix 1, 5, 2, 0, 4, 7, then A is a 2x2 and B is a 2x3. So we can multiply A times B, which would be 1, 3, -1, 0 times 1, 5, 2, 0, 4, 7. And the result will be a 2x3 matrix. And here's how I get it. I take the rows of the first and the columns of the second. So for the 1, 1 position, I take the first row and the first column. That's 1 times 1 plus 0 times 3. To figure out the 1, 2 position, I take the row of the first and the first row and the second column. So that's 1 times 5 plus 3 times 4. To get the 1, 3 position, I take row 1 and column 3. So that's 1 times 2 plus 3 times 7. Now I go down to the second row here. I'll be taking row 2 and column 1 for this guy, row 2 and column 2 for this guy, row 2 and column 3 for this guy. So that's -1 times 1 plus 0 times 0. That's row 1 and column 1. Now for the position here, I take row 2 and column 2. So that's -1 times 5 plus 0 times 4. And to get the 2, 3 position, I take row 2 and column 3. So that's -1 times 2 plus 0 times 7. And this I can then do each little bit of arithmetic. 1 times 1 plus 0 times 3 is 1. 1 times 5 plus 3 times 4, that's 5 plus 12 is 17. 1 times 2 plus 3 times 7 is 2 plus 21 is 23. 1 times -1 plus 0 times 0 is -1. -1 times 5 plus 0 times 4 is -5. -1 times 2 plus 0 times 7 is -2. So this is matrix multiplication. And like I said, horrendously complicated operation compared to, what you might think it means to multiply two matrices. There's very good reasons why matrix multiplication is defined this way. Question: can we multiply b times a? That would be 152,047 times 1, 3, -1, 0. This is a 2 by 3. This is a 2 by 2. So I can multiply a times b. Can I multiply them in the other order? Does b times a even exist? No. Yeah, because these inner numbers don't match. N is not equal to p, so a times b, or sorry, b times a can't be formed. This does not exist. No such thing. So matrix multiplication, kind of the first lesson here is it's not commutative. In real numbers, x times y is always the same as y times x. 2 times 3, 3 times 2. I don't give a shit. Matrices, you give a shit. A times b is not always the same as b times a. Even if both can be formed. So here we saw in one direction you could do the product, in the other direction you couldn't. You might ask, well, what if you can do both products? Then are they the same even then? Nope. The slick way of solving a system is to rewrite it as a matrix equation, and then you kind of divide by a matrix. So let me show you what I mean. And this is really cute, but you are very in the way, Bubba. So let me take a system which I know to be consistent. Let's do something simple. 2x minus 5y equals 7. And 3x plus 2y equals 4. This can be written as the matrix equation to -5, 3, 2 times the matrix little x, little y equals matrix 7, 4. You can check, right? Because if I multiply this times this plus this times this, the left-hand side is 2x minus 5y. And then here I'd have 3x plus 2y. And as a matrix, that's equal to 7, 4. So this system is true if and only if these two matrices are equal. Because here I would need the first entry of this matrix, right? This is a 2 by 2. This is a 2 by 1. So the result here is this 2 by 1 matrix. So this is equal if and only if this is equal to this, and this is equal to this. In general, two matrices are equal if they are the same size, same dimension, and all same entries. So when I say that this matrix equals this matrix, I mean 2x minus 5y equals 7, and 3x plus 2y equals 4. But that's the same as the statement of this system. Okay. So let me call this matrix A, 2, minus 5, 3, 2. Let me call this matrix capital X, and I'll maybe put some feet and stuff on my X to make it look more like a capital letter that's got the entries little x, little y. And let me call the matrix capital B, 7, 4, like this. Then my system is equivalent to the matrix equation is what we just checked, AX equals B. And if these were numbers, if A and B were numbers and X was just a regular variable, I would solve that equation by dividing both sides by A. Now, unfortunately, while there is a concept of multiplication for matrices, there is no such thing as division. The closest you have is what we call an inverse matrix. So we can solve this matrix equation by finding a special matrix called A inverse, which satisfies A inverse times A equals I, where I is the identity matrix. In this case, it would be I2. And A times A inverse equals the identity matrix. In this case, again, I2. Then multiply both sides of the matrix equation AX equals B by A inverse on the left, giving A inverse AX equals A inverse B. And since A inverse A is I, in this case I2X, equals A inverse B. This times this is I, and I times anything is just that thing. You would get here just X equals A inverse B. Now, Finding inverse matrices is a pain. I'll show you how to do it. I'll do it once here. I don't expect you to do it by hand, but I do expect you to know what an inverse matrix is and know how it's useful for this process. Let's solve this system. I'm going to begin by writing it like this. So here, solve 2x minus 5y equals 7, 3x plus 2y equals 4 by finding an inverse matrix and using matrix multiplication. The way you find an inverse matrix, so our original matrix A here, so this system is equivalent to AX equals B, where A is the 2 by 2 matrix, 2, -5, 3, 2. X is the 2 by 1 matrix, little x, little y, and B is the 2 by 1 matrix, 7, 4. Oh, sorry, we want to go back for a second. We're here. So the game is to find this special matrix A inverse. Then you take your matrix equation, AX equals B, multiply on both sides by A inverse. The A and A inverse cancel, so you just get X equals A inverse times B. You compute that product, that will be the matrix of your answers, X and Y. Okay. So this is a time-consuming process, so I'm going to go ahead and do it. To find A inverse, you can only do this for square matrices. Remember, a square matrix is like a 2 by 2 or a 3 by 3 or a 4 by 4. This is a square matrix. We augment by the identity and row reduce. So I take A augmented by I here, that is 2, -5, 3, 2, augmented with the 2 by 2 identity, 1, 0, 0, 1. And you row reduce this all the way to reduced row echelon form. You row reduce this until you have the identity over here, then this will be A inverse. It's a nasty process. My first step would be to divide through row 1 by 2. So my new row 1 is 1/2 my old row 1. Get ready for some fractions. 1, -5/2, 1/2, 0, and then the bottom row stays the same, 3, 2, 0, 1. Then I need to kill the 3 in this position, so my new row 2 is -3 times old row 1 plus old row 2. Row 1 stays the same, 1, -5/2, 1/2, 0. Multiply this by -3 and add it to this, you'll get 0. Multiply this by -3, you get positive 15 halves. 15 halves plus 2 is 15 halves plus 4 halves. 15 plus 4 is 19, so that's 19 halves. -3 times this is -3 halves. -3 halves plus 0 is -3 halves. And 3 times this is 0 still, so this guy stays a 1. Now I've got a 1 in the pivot, a 0 below. I need to make a 1 here. So to do that, my new row 2, I'll multiply by the reciprocal of this. That's 2 over 19 times my old row 2. Row 1 stays the same, 1, -5 halves, 1 half, 0. Row 2 will become 0. 19 over 2 times 2 over 19 is 1. -3 halves times 2 over 19 is -6 over 38. Is that right? Yeah. And 2/19 times 1 is 2/19. You see there's plenty of room to make little mistakes here, especially when we're dealing with these fractions. Now my very last step would be to kill this -5 halves. So my last row operation here, my new row 1 is going to be +5 halves times row 2 plus old row 1. I want to multiply this by 5 halves and add it to that to make a 0. Row 2 isn't going to change. It's going to stay 0, 1, -6 over 38, 2 over 19. And then row 1, 5 halves times this plus this is still 1. 5 halves times this plus this is 0. Get ready for the nasty algebra. I may borrow a calculation tool here. 5 halves times 6 over 38. So we're doing 5 halves times 6 over 38, and this is negative. And I want to add that to 1/2, which is not a nice number, 2/19. Oh, that's relatively nice. That's surprisingly nice, yeah. So come back here. 5 halves times this plus this, that's the thing we just computed, is 2 over 19. So what goes here is 2 over 19. And then the last thing we need to do is 5 halves times this plus this. So that's enter. Now I need 5 halves times 2 over 19 plus 0, which as a fraction is 5/19. Now let me come back. That was our last row operation that we needed to get this into reduced row echelon form. So A inverse is the matrix that shows up on the right here. 2/19, 5/19, 6/38 is definitely simplifiable. What is 6/38? It's also a ratio over 19, 3/19. This is -3/19, and this is 2/19. And finally, AX equals B is equivalent to A inverse AX equals A inverse B. A inverse times A is the identity, so we just get X equals A inverse, which is 2/19, 5/19, negative 3/19, 2/19 times B, which is 7/4. And now if you carry out this matrix product, you will get your answer. Now some good news. There's a factor of 1/19 that can come out here. And that just leaves me with 2, 5, negative 3, 2 times 7/4. That's a lot easier to work with. So this is 1/19. Now I need to do this product. So 2 times 7 plus 5 times 4. And then negative 3 times 7 plus 2 times 4. And it's a 2 by 1. This is 1/19 times 14 plus 20 is 34. Negative 21 plus 8 is 21 minus 8, 12, 13. So the matrix X, which is our matrix of solutions, is 34/19 and 13/19. And remember what this was. This is little x, little y. So little x is 34/19 and little y is 13/19. Those are the solutions to this system. I realized that nobody in their right mind would jump in to solve that 2x2 system this way. That was an awful lot of work to solve a silly little 2x2 system of equations that you've known how to solve probably since 8th grade. The good news is, as the matrices get larger, this doesn't get harder. So while this might seem like a lot of work to solve a 2x2, it's not really a lot of work to solve a 10x10, or 100x100, or 1000x1000 system. The amount of work it takes to invert a matrix doesn't really go up a lot with the size of the matrix. Which means that for solving big systems, this is a good method. If you have to solve a system by hand, I think the sweet spot is writing it as an augmented coefficient matrix, and then putting that into upper triangular form, like we said at the start of class today. But this business of finding inverse matrices is a big deal. And it's a big enough deal that I want to show you a shortcut for inverting 2x2 matrices. It requires you know something about a determinant. Given a matrix A, given a square matrix, there is a number called the determinant of A, which is useful in finding the inverse matrix. For 2x2s, I'll call it A, B, C, D. the determinant is just the product of the main diagonal minus the product of the off diagonal, AD minus CB. And if you know that, the shortcut for a 2x2 is this. A inverse is 1 over the determinant of A times the matrix you get by switching these guys and negating these guys. So it's D and A here, and then negative C and negative B here. Let's try that on the matrix we just inverted. There's a number called det. It's DET and then parentheses A. Det is really a function. It takes in matrices and spits out numbers. So this is the symbol for the determinant, DET of A. Short for determinant of A. I know this is a lot. You guys are doing good. Linear algebra is scary when you first meet it. If you take the time to study this stuff, and it really does require a lot of time, linear algebra is actually one of the most beautiful subfields of mathematics. It's one of these places where we really know everything that there is to know. And it can be so useful. So the matrix A from the last problem was 2, -5, 3, 2. The determinant of that matrix is 2 times 2 minus 3 times -5, which is 4 plus 15, which is 19. That's why we had all those 1 over 19s. That's where this came from. It's really this, the 1 over the determinant of A. So by our shortcut for 2x2 matrices, A inverse should be 1 over 19 times, what do? We switch the main diagonals. So the main diagonals were both 2, so I switch those, they don't change. And then I negate each of these. -5 is +5, -3 is -3, which is 2/19, 5/19, -3/19, and 2/19. And if you compare that to what we had before, here it is, they're the same. So this shortcut gets you around the row reduction. Only works for 2x2s, unfortunately. All right, you guys are doing great. You've made it through the hard part. The last thing I want to show you here is simple stuff, how to add, subtract matrices, multiply them by numbers. Unfortunately, there is no shortcut for inverting a 3x3. Before I show you the boring stuff, I'm going to show you a utility here. Symbolab has one, matrixcalc.com. I think this is the one I've used in the past that I liked more. Yeah, I don't like Symbolab. But if you want to invert a matrix, you want to do any sort of operation to a matrix, I can ask this to compute an inverse, and there it is. Simple, simple stuff. And you can look at the details. What we're using is the Gauss-Jordan method, where you augment by the identity and row reduce. I don't have a problem with you guys seeing this. Right? It's a bit of a cheat, but nobody should really do matrix inverse calculations by hand anyway. They're horrible. You saw me just do a 2x2. It was unpleasant, even for me. So I'm all right with you guys using a tool like that to invert a matrix. I won't ask you to invert a matrix on the test. But I do want you to know what a matrix inverse is, and I want you to use it in the homework problems that call for it. Last thing for today, determinants of larger matrices. Actually, you know what? Fuck that. No, that's brutal, and you don't need it. I'll omit this, but you do need basic algebra of matrices. All right, so if you want to add two matrices, we'll start with multiplication by a number. Multiply any matrix by a constant according to the rule, just by multiplying all its entries by that constant. For example, if I want to multiply the 3x3 matrix 1, 0, 2, 0, negative 1, 7, 3, 0, 1 by the constant 5, I just multiply every single entry here by 5. 1 times 5 is 5, 0 times 5 is 0, 2 times 5 is 10, 0 times 5 is 0, negative 1 times 5 is negative 5, 7 times 5 is 35, 5 times 3 is 15, 5 times 0 is 0, 5 times 1 is 5. Doesn't matter the size. We can add or subtract two matrices only if their dimensions match exactly. So like 1, 0, 2, 0, 3, 7 can be added to 0, 2, negative 1, 1, negative 3, 5, because they're both 2x3s. The first and second numbers are the same, so now we can add these, and you just add them component-wise. So 1 plus 0 is 1, 0 plus 1 is 1, 2 plus negative 1 is 1, 0 plus 1 is 1, 3 plus negative 3 is 0, and 7 plus 5 is 12. You just add each by adding matching entries called the components. Same for subtracting. If I want to subtract from 2, negative 3, 5, 7, the matrix 1, 0, 0, 1, I can do that because they're both 2x2s. And I just subtract them component-wise. So 2 minus 1 is 1. Negative 3 minus 0 is negative 3. 5 minus 0 is 5. And 7 minus 1 is 6. Multiplication by constant, addition and subtraction, those are not complicated for a matrix. What is complicated is multiplying a matrix by another matrix. And taking determinants. Determinants are also pretty complicated. Normally in this class, I would include a discussion of 3x3 determinants and higher determinants, but the truth is you don't need that shit. You're not going to use that until you get to the end of Calc 3. And in that setting, they will show you how to do it. It's not challenging. If you want to research it, I'll let you. But since you guys were so wonderful to come here on the day before Thanksgiving, and since there is only 5 of you, I don't think it's fair to drop any heavier bombs than we've already dropped. So matrix multiplication, important. The concept of an inverse matrix, very important. More important than any of that, though, is that you get comfortable doing row operations, right? The stuff that we were doing on Monday that we introduced through systems. So please work on these things in the homework next week. Rather than beating you to death with more and more matrix stuff, I want to talk about sequences in series. We need to spend some time on that before the course ends. There's one other topic that I usually like to include on conic sections, but a detailed study of conics we'll just have to let go of this semester. It's one of the faults of the coronavirus. There's nothing in there that's important to calculus, thank goodness. It's just something that's fun to talk about in pre-calc because it kind of fits. The matrix algebra stuff is very important to calculus, but only the things that we've done. So I'm trying to strip this class down to its necessities for you guys. So next time we're going to talk about sequences in series. I might do a little recap on some of this matrix stuff for the people who missed here today. But that's going to be it. All right, we'll talk about sequences in series next week, and that will be the end of the class. I'm thinking probably in order to avoid shortchanging the sequences in series stuff, exam 4 will be a take-home. So I'll give you exam 4 as a take-home exam, and I will do that on Wednesday of next week. And then your final, again, your final exam for this class, which is comprehensive, will cover everything, is going to be on, this is you, right? 1140. Your final is on December 7th from 3:30 to 5:30. Alrighty? So again, thank you guys for coming today. I hope you enjoy this matrix stuff. I recognize that it feels like it's out of nowhere and it can be a little overwhelming. But take a look at the resources I have up for you in Canvas. I'll post a few more in case you're curious. It's a really beautiful area of mathematics that if you go into higher math or you start studying higher physics, you'll use a lot of. Yeah, happy Thanksgiving to you guys. Take care of yourselves. Please be safe, and I will see you on Monday.